My name is Albert Rodriguez, and I'm a battery applications engineer at MPS since 2019. I hold a Master of Science and a PhD with special focus on battery controls, and I am mainly involved in modeling, simulation, and identification of battery systems, including the development of MPS Fuel Gauge algorithm.
Hello, my name is Miguel Ángel Sánchez. I will be co-presenting this webinar with Albert. I'm a battery applications engineer at MPS, and I'm mainly focused on creating reference designs and complete BMS solutions, as well as defining new products and architectures. I'm also the technical point of contact in Europe and US. In this webinar, we are going to be focused on explaining the key considerations when designing a battery management system. But prior to that, we first need to understand what are the main tasks of a battery management system, or BMS. The first and more known is monitor and protect the battery against any possible failure. However, among the responsibilities of the BMS, we also find balancing the cells to make sure all of them are at the same level of charge, estimate the state of charge and the state of health of the battery, as well as interface with the system. Apart from that, depending on each application, we can have a specific dedicated task, such as proprietary communication protocols. There is a wide range of components in the market that help to achieve these tasks, so it's important to understand the key components and what is the added value of each one before making a decision. This webinar main goal is to help the designers to understand what to look for when making this decision. Rechargeable battery systems are expanding into a growing range of applications. Nowadays, almost all electronic devices include a battery. But today, we're going to discuss battery management systems architecture that fits these main markets. These applications typically require from 7 to 32 series cells. The battery management system for these specific systems are typically designed on a single centralized printed circuit board, or PCB, based on industrial standards, highly focused on cost, and a high level of integration. Each class of application has unique as well as overlapping requirements. For example, power tool markets requires a very high rate of instantaneous power. This is why power cells are mainly used. For the UPS or backup batteries, an important topic is parallelization, since the batteries are connected and disconnected on the fly depending on the power demand. In this case, a very accurate state of charge is key for better performance. In the energy storage market, since the voltage range can be between 48 volts up to 1000 volts, scalability designs become essential. The basic diagram shown here is the battery management architecture proposed for the mentioned markets. In the case of the high voltage energy storage market, the architecture changes a little bit, since we need to stack several battery monitors to go up to 1000 volts. In any case, the main elements of the BMS to be discussed today consist of a battery monitor and protector, an MCU, and a field gauge IC. The battery monitor and protector is in charge of measuring all the voltages, temperatures, and currents of each cell, making sure the battery is within the safety operating area. For making sure this, it usually controls the protections of the battery. Then we have the main microcontroller, or MCU, that acts as an intermediary between the battery monitor, the system, and the field gauge. Finally, we find the field gauge IC, which estimates the different battery parameters. Having a separate IC and not embedding the field gauge algorithm within the MCU reduces the resources demand of the MCU, and therefore a cheaper MCU can be used. It also increases the robustness of the system in corner cases, since this device comes fully tested in all possible scenarios, as well as ensuring a faster time to market. Once the proposed architectures, along with the key components of the BMS, has been explained, we're going to center this part of the webinar on explaining what are the features to look for in every of these devices, as well as their main functionalities. The first device we're going to explain is the battery monitor and protector. the one that is sensing all the voltages, currents, and temperatures of the battery. So what it does with all this data? Well, we can separate three primary tasks to be performed with this data. The first primary task is analyze to determine if the battery is operating within the safety operating area. In this case, a fast response is much more important than high resolution results. If the battery is out of this safety operating area, the battery monitor must be able to detect it and act accordingly. For this, the battery monitor usually has a very wide set of configurable faults in which we could highlight the following as the most important ones. First of all, we have the short circuit and overcurrent detection, in which the designer should look for devices with analog comparators that are able to detect these situations as fast as possible. Then we find the cell and pack overvoltage condition. This one is one of the most critical faults that can happen within a battery. So designers should make sure that the device selected has the appropriate mechanisms to detect it. And finally, we find the over and under temperature fault, which are also important. After detecting any of these faults, is a huge advantage if the battery monitor and protector can directly control the protection's FETs. Having this direct control using an integrated high-side FET driver ensures a better protection of the battery. The second task is ensure that the cells operate within a controlled range of operation, generally using passive balancing. Passive balancing is accomplished by enabling a discharge path across any cell with a charge that is significantly higher than the lowest state of charge. A resistor is used in this discharge path to set a controlled amount of current. Internal passive balancing may be enough for most cases, but sometimes if more balancing current is needed, external balancing with external switches and resistors can be used. In any case, the battery monitor can directly control passive balancing or follow the commands of the MCU. That's up to the designer. Apart from the passive balancing, active balancing is also possible in these systems, especially in energy storage. Active balancing moves charge from one cell into another with almost no charge loss. The last task would be what we call take high-resolution measurements. These are the ones that are used later for doing battery estimations in the field gauge. Within these high-resolution measurements, we find the cell and pack voltages, cell and pack current, and temperatures. The frequency of taking these measurements depends on each market requirement, and it's also up to the designer. Although these are the most important tasks of the battery monitor, it's also important to select a battery monitor that accounts for watchdog, easy communication protocols, extra GPOs, safety features, among others. After understanding what the main functions of the battery monitor and protector are, we should explain a little bit more about the key features all designers must consider when designing which battery monitor select. The first one is the integrated high-side driver that can directly control the power FETs without external circuitry. Thanks to this high-side integrated driver, in MPS, we developed what is called a soft start functionality, which eliminates the need of using a pre-charge or pre-discharge circuitry. This is because slowly ramping the gate voltage of the FETs, we can charge the capacitor of the application load, controlling the amount of current flowing through the FETs. In other words, we operate the FET in its linear zone, limiting the current that is flowing to the capacitor's load to elevate the voltage in the load side. So we can fully close the protections, as can be seen in the right plot. Of course, when we reach the battery voltage, we close completely the protections to allow the full current discharge. Another interesting topic is about synchronous reading. Some battery monitors have 2 or more ADCs for taking voltage and current measurements separately. These ADCs can be synchronized in order to take cell voltages and cell current measurements at the same time. This feature helps later the field gauge for equivalent series resistance estimation, which directly impact to important battery estimations, as we will see later. The last key feature worth mentioning is the hardware protections. It's important that the battery monitor and protector can disconnect the battery as fast as possible from the load or charger once a fault is detected. As mentioned before, the battery monitor should be the one directly deciding when the protections must be open, ensuring a better protected battery. With any of the faults previously mentioned, for example, with the overcurrent, the battery monitor should be able to detect it, act over the protections, and then notify the MCU. Once explained the battery monitor and protector, we switch to the microcontroller or MCU. As it's shown in the diagram, we can differentiate 4 different blocks within the MCU that defines the primary task of it. The first one is data processing. The MCU acts as the master of all communications within the BMS. So it asks for the data to the battery monitor, processes data, making all the needed conversions, and send it to the field gauge every time it's needed for battery estimations. So the MCU shall have the typical protocols for connecting with both the battery monitor and the field gauge. These protocols are usually SPI or I2C. The different actions performed by the MCU, the battery monitor, and the field gauge is determined in the main state machine block, which can be understood as a scheduler. Then the MCU executes its function every time it's needed, depending on the system state and depending on the demands of the designer. As mentioned before, the BMS also connects with other systems in the overall application. The MCU is usually the one managing these communications, as for example in an e-bike. This communication is usually CAN or RS485, but other can be used as well. Finally, some redundancy safety checks are usually performed after data processing within the MCU. It can be programmed to double-check possible overvoltage, undervoltage, or any fault, in case the battery monitor was not able to detect them properly. This good practice also helps to detect if the battery monitor is properly working, increasing the safety level of the complete BMS. Without a separate field gauge IC, field gauging algorithms are generally included into the MCU. If so, the field gauge block would be the biggest and most demanding within the MCU. With a separate field gauge IC, a lower cost and less powerful MCU will be sufficient to perform all the mentioned tasks. Now, I will hand it over to my colleague Albert, that is going to explain more about field gauges.
Thank you, Miguel. In the following slides, I would like to answer a couple of common questions. Why do batteries need a fuel gauge in the first place? And how valuable is the information it provides? First, let's cover the basics. The fuel gauge is responsible for estimating battery internal variables, such as state of charge, that represents the level of charge relative to the battery capacity. By accurately knowing the battery's state of charge, or SOC, we can estimate how much energy is available, balance individual cells to extend runtime, and control the SOC range used to mitigate degradation, among others. The state of charge is not directly measurable and therefore must be estimated from measurable quantities such as current, voltage, and temperature. For example, one simple method to estimate SOC is to use Coulomb counting, in which battery current is measured and integrated over time to calculate the amount of capacity remaining inside the battery. Assuming that we can start at a known state and we can measure current, this should give us an approximate SOC estimate. However, a good understanding of lithium-ion characteristics that capture the relationship between the measurable quantities and the state of charge can significantly improve the accuracy of the estimates. For example, another simple method to estimate SOC is to use the open circuit voltage, or OCV, which maps the battery voltage at equilibrium to SOC. Hence, we can create an empirical OCV dataset by measuring the open circuit voltage over the operating SOC range and repeat that at multiple temperatures to provide a family of OCV curves that cover voltage and temperature characteristics. Then, by comparing the measured voltage on a cell in an open circuit condition, one can estimate the SOC. Nonetheless, higher SoC accuracy can be achieved by using more advanced methods and higher fidelity cell models derived from comprehensive characterization of the battery cell. These models will not only model OCB, but will also capture other very important dynamics, such as impedance, as we can see in the bottom right plot, that shows the real and imaginary parts of the battery impedance for a wide range of frequencies, and hysteresis, where the open circuit voltage depends on the history of the battery, as depicted in the OCB plot in the bottom center. Note that battery behavior changes depending on the operating conditions, so accurate modeling in the complete range of operation is needed. Consequently, accurate battery modeling becomes a time-consuming, resource-demanding task that requires deep understanding of lithium-ion battery dynamics. For the purpose of helping customers achieve superior performance while minimizing effort, resources, and complexity, MPS has developed an internal characterization routine and built proprietary cell model extraction tools to offer a turnkey solution. Let's now compare the pros and cons of estimating state of charge by using three different fuel gauge methods: the Coulomb counting or CC method, the Coulomb counting combined with OCB-based corrections, and the MPS hybrid method. Let's start with the simplest method, the Coulomb counting approach. This method is very easy to implement and requires minimal data to estimate SOC. However, it is unable to recover from inaccurate initial state of charge estimation due to the lack of voltage-based feedback. More importantly, any error in the current measurement will cause the SOC to accumulate and therefore drift over time. In order to solve the SOC drift over time, the Coulomb counting method is commonly combined with corrections based on the open circuit voltage of the specific battery cells. However, the second method also has some shortcomings. First, the corrections accuracy will depend on the open circuit voltage characterization accuracy and the measurements accuracy. Therefore, errors in the OCB characterization and cell voltage measurements will greatly impact this method. And second, the corrections may be infrequent, since they only occur during relaxation periods. These will cause SOC jumps that can create system-level problems and negatively affect the end customer. Ideally, the state of charge correction should be small and continuous to ensure the estimated SOC always tracks the true SOC, since this will improve the overall performance of the system. MPS hybrid method achieves this by combining multivariable cell characteristics such as voltage, current, temperature, and aging, together with a high-fidelity model that captures the battery's most important dynamics in its complete operating range. Furthermore, the algorithm optimally corrects the state of charge based on the current operating conditions and by accounting for model and measurement potential inaccuracies. This limits the need for very high accuracy on any single parameter, such as cell voltage measurements. One of the challenges of using such approaches is to accurately model battery cells. However, MPS overcomes this by providing the appropriate cell-specific high-fidelity model. Hence, customers using MPS fuel gauge turnkey solution will be able to achieve excellent performance with minimal effort in minimum time. So far, we have seen different methods for estimating cell state of charge, but highly accurate fuel gauges such as the MPS hybrid method can provide much more. Battery packs are built from multiple cells connected in series that may be operating under different conditions. For example, individual cells may be at different state of charge levels, operate under different temperatures, and the cell's capacity and resistance may diverge over time due to aging. Hence, pack level quantities such as pack state of charge are not trivial, since they will depend on the cell level quantities and the application usage. Thus, the fuel gauge must use the current individual cell states, parameters, and operating conditions represented by the green arrow in the diagram and find out the fully charged state of the battery that defines the 100% pack state of charge by projecting how the battery will be charged, such as common CC/CB charging, according to the charger settings. This is shown in red color in the diagram. and the fully discharged state of the battery that defines the 0% pack SOC by projecting how the battery will be discharged according to the load characteristics. And this is shown in the blue color in the diagram. However, note that these are instantaneous projections that continuously change depending on the battery states, parameters, and operating conditions. As a result, an accurate fuel gauge must continuously reassess and refine its SOC estimates. Besides the pack SOC, the fuel gauge can also provide other variables of interest that can help optimize the battery pack performance, such as the estimated runtime, which is key to know how much time the device can be operated before shutting down, or the estimated charge time, which indicates the time required to fast charge and fully charge the battery. Note that cold temperatures can drastically reduce available energy, so up-to-date information about remaining time is fundamental. Another key variable of interest is the maximum available power the battery can deliver or accept before reaching the safety operating area limit. Accurate power limits can help transition from high power to low power modes depending on current operating conditions to increase usable energy and therefore extend runtime. One more important feature is the ability to track capacity fade and resistance rise of each individual cell connected in series, since this will directly affect the total energy available in the battery and limit the power capabilities. In summary, MPS hybrid method provides battery key insights that can be used to extend runtime, increase range, achieve longer lifetime, and improve designs. We have seen that accurate estimation of battery internal variables such as the state of charge are key for any battery-powered applications, since poor SOC estimations may cause system-level problems and negatively affect the end customer. In the previous block of this webinar, we discussed the main advantages and disadvantages of using different fuel gauging methods. However, they all have something in common. They rely on battery measurements to some extent. Therefore, it is important to understand what is the impact of the battery monitor measurement accuracy and the fuel gauge method to the accuracy of the estimates like the state of charge. In this block, we are going to cover the key considerations when selecting the battery monitor and the fuel gauge. A solid understanding of how battery measurement accuracy influences the state of charge accuracy will help BMS designers optimize the trade-off between SOC accuracy and cost. Oftentimes, BMS systems target expensive battery monitors with extremely high voltage accuracy to achieve good SOC estimation accuracy. However, the fuel gauge method plays a major role in improving the state of charge results, as we can see in the figures. On the left figure, we show the peak state of charge error as a function of the battery monitor voltage accuracy for nickel manganese cobalt lithium ion chemistry, or NMC. The color bars in the plot correspond to the three different methods presented earlier. That is, the Coulomb counting method in pink, the Coulomb counting plus OCB-based corrections method in green, and the MPS hybrid method in blue. On the right figure, we show a similar plot, but in this case, we show the results for lithium iron phosphate chemistry, or LFP. Note that the state of charge estimation is more challenging for LFP due to the flat open circuit voltage and hysteresis. The Coulomb counting method, shown in pink, relies on voltage only on the initial state of charge estimate. Therefore, any error on the initial SOC will not be corrected since it runs open loop. Additionally, any error in the current measurement will cause the SOC to accumulate and therefore drift over time. For these reasons, the Coulomb counting method does not provide good results. On the other hand, the Coulomb counting plus open circuit voltage-based correction method, shown in green, relies on voltage measurements only during relaxation, where cell voltages converge to the open circuit voltage. Results of this method outperform the Coulomb counting method since it can correct the SOC drift over time. However, these corrections are affected by the voltage measurement error, the relaxation times, and the open circuit voltage characterization. Relatively short relaxation times can cause inaccurate corrections because cell voltages have not yet converged to its open circuit voltage. This is particularly relevant for LFP chemistry because of its flat open circuit voltage. For example, if we look at the LFP results on the right figure, we see 0 millivolts voltage error does not produce the best results in this case. Finally, we see the best results are produced by MPS hybrid method in blue, since it periodically combines voltage, temperature, and current measurements and a high-fidelity battery model to make optimal state of charge corrections. MPS's hybrid method is also the most robust method since it considers measurement potential inaccuracies when applying these state corrections. Moreover, MPS's hybrid method can estimate capacity fade and resistance rise of every individual cell connected in series, in order to track how cells in the battery pack age over time and keep the battery internal estimates, such as SOC, accurate. In summary, battery measurements accuracy clearly influence the state of charge accuracy, but the fuel gauge method used is really the key to achieve good results. In this webinar, we talked about the key considerations when designing a battery management system, or BMS. In the first block, we introduced the main tasks and responsibilities of a BMS and how different target applications may have distinct BMS requirements. Then we presented an example of BMS architecture to introduce what are the key components. In the second block, we explained in more detail each of the key battery management system components. The battery monitor and protector, where we covered primary functions and key features such as the soft start function and the synchronous voltage and current measurements. We also covered the main MCU, where we explained the core blocks and main tasks, and the fuel gauge, where we looked at different methods for estimating state of charge, from the simplest Coulomb counting approach to the highly accurate MPS hybrid method. Then, in the third block, we saw that battery monitor accuracy is not the only factor affecting state of charge accuracy, and the fuel gauge method is really the key to achieve excellent performance. In summary, the design of battery management systems is a complex task since it involves critical safety functionalities and a good understanding of battery dynamics. All of this while achieving low cost and short design time. MPS offers a wide range of battery monitor and protector ICs, the MP279X product family, and fuel gauge ICs, the MPF427-9X product family. Customers interested in evaluating our solutions can request our standard BMS reference design board for 7 to 16 series connected cells, which is shown in the top left, or the stacked MP279X board for 17 to 32 series connected cells, which is shown in the top right. Besides that, MPS provides a step-by-step user guide, an easy-to-use graphical user interface that can be downloaded from our website at monolithicpower.com. Additionally, MPS also makes the firmware of the main MCU available for easier integration of our battery monitor and fuel gauge ICs. For customers interested in achieving faster time to market and avoid dealing with BMS design challenges, MPS also provides support in all development phases, including cell and component selection, design, configuration, and validation according to customer requirements. An example of MPS's complete solution board ready for production is shown in the bottom right, capable of providing 100 amps of continuous current and 180 amps of peak current. To conclude, we would like to thank everyone for your assistance. We hope you found the content of this webinar useful for your current or future battery management system projects. Now, we will be happy to answer your questions in the Q&A session.
Thanks, Albert and Miguel. Lots of good information today. Once again, if you mouse over the Zoom webinar interface, there's a Q&A button. You can click on that and then just type in any questions that you have. As we're waiting on questions, a reminder, we have been recording this session. It will be available on demand within the next couple of days, and we will email that out to you by the end of the day. You can always find our past webinars at monolithicpower.com/webinars. All right, it looks like we've got one here. It says the MPS hybrid method seems very complex. How easy is it to configure and implement for customers?
Yeah, that's a great question. MPS Fuel Gauge algorithm is very easy to use and only requires basic battery pack information. However, advanced configuration is also available for more experienced customers that want to have more control. MPS provides a user-friendly graphical user interface that makes configuration and evaluation quick and easy, including virtual fuel gauge simulations to reduce battery testing.
Great, thank you. Next one here. How long does it usually take to go from a specification to a fully working custom solution?
It usually depends on the expertise that you may have, but with our drop-in solutions and all the material that we share with customers, we usually say that within the range of 3-6 months, you can go fully operating with our ICs. As we mentioned at some point, we send all the reference design files, we share libraries, and the Fuel Gauge is literally a drop-in solution that it's very, very, very easy to configure.
Great, thank you. And the next one, how many cells can one stack at the most using the MPS solution?
Yeah. So it depends on the different architectures that you are looking, and it depends on the ICs that you will use. For example, the MP2787 can be stacked for example, a 1000 volts application. We can share more information about the different architecture with our different ICs. So please feel free to contact us and we can send you this information later, and we can talk about your desired architecture, because with the ICs we can cover almost all configurations.
Great. Next one up was, can you add supercapacitors to this design for a hybrid quick charge configuration?
So in terms of the fuel gauge basically receives all the measurements that are taken by the battery monitor, and then the MCU processes this data and send it to the fuel gauge. So as long as this charging can be used for the processing of this data, we can account for that using our fuel gauge IC. However, we would need more details to give you a more detailed explanation, so feel free to contact us and we can discuss this particular case.
Thank you. And then there's another question about, so yes, we're recording the session via video, but the presentation packet will be available as a PDF, and yes, we'll send that out to you by the end of the week as well. So thanks for asking. Next one, while using the MPS BMS solutions, is it possible to get the battery characterization from MPS or to Branchmark?
So yeah, we have explained in the presentation, the battery model is one of the keys to achieve excellent performance. So we have developed our own sequence at MPS in order to be able to capture all the most important dynamics of the cell. So when requesting a fuel gauge, we have available a cell model database where you can look for your specific cell model. And if it is already in the database, it is as simple as selecting the model and loading it into the fuel gauge. If your particular cell model is not in the database, then we can characterize the cell for you. So basically, we run our own sequence to characterize and generate a new cell model that's specific for this particular cell. Additionally, we also have like a third option, and is that we basically can identify and provide the closest model available in the database in order to make the evaluation process quicker.
Great, thank you. Another one just came in. Can the communication bus between the BMS be an EtherCAT bus?
Yeah, so since the communication with other BMSs or with the system is managed by the MCU, if the MCU has this interface, it's totally possible. We mentioned CAN and RS for 85, but it's not limited to this. So yes, you can use Ethernet or EtherCAT bus for communicating different BMSs within the same system.
All right, thank you. All right, I think that is all the questions I had seen. We still have more time if you had any additional questions. Oh, well, we got to thank you. But we'll just pause for a few more seconds here to see if any last minute questions come in. I'm not seeing anything coming up. Oh, here it came last second. Can MPS stack more than 32 ICs?
Yeah. So as I told before, it depends on the ICs that we are talking about. For the MP2787, it's possible. So if you want to know more about this, you can send to us an email and we can have a separate meeting, or we can share with you different architectures, because we need to understand first what's the architecture of the system so we can give better support and how it's better to stack these ICs.
All right, thank you. All right, I'm not, oh, they keep getting us right at the buzzer. Could you provide a formal instruction set for battery profiling to your customers?
So for the battery characterization, let's say there are like two different phases. We have the characterization step where we basically run multiple tests to the physical battery. And then we have the model extraction tool that basically takes this data and generates the cell model that's expected by the fuel gauge. So for the first portion, we have our own sequence. So that's something we can work for the customer if they are interested in knowing more and work together in order to speed up the model generation. And then for the second phase, that basically takes this data as input, we consider that proprietary, so we can generate that for you. And then, as I said before, the new cell model will be generated and you can load it into your fuel gauge to be ready for estimating the different battery internal variables.
Got a couple more in. Do you have an FPGA version of your MCU plus fuel gauge system?
Not right now. As we say, at some point, having the fuel gauge as a separate IC ensures that it performs with higher accuracy over time and temperature. It reduces the time to market and enable other features difficult to implement within an MCU. So if you have all the MCU or the MCU open to the customers or the field gauge algorithm itself, it's going to be harder to validate every time you change anything for your MCU. That's why we decide to have a separate IC for the field gauge and then the MCU within the system.
Okay, thank you. And then, does MPS have a solution for interpack active balancing?
Not at the moment. We have solutions for active balancing between cells, and we are working hard in that direction. So right now for interpack active balancing, we don't have a part right now, but you can contact us and tell us more about your specifications, because we will probably have something that could fit your application.
Okay, and then different person, but somewhat. Do you need to do inter-pack balancing if you have a distributed battery pack architecture?
That's a good question. If you, for example, have if you have balancing or active balancing with, like, in every cell, right, or in every pack, it should ensure that all the cells are at the same charge. So you won't need at the end this inter-pack balancing, since you are already balancing within the same pack all the cells.
And then, guys, you've mentioned, reach out to us. Is there a best way to contact you guys for a little bit more follow-up on these topics?
Yeah, you can reach out through the Monolithic Power webpage, or you can ask directly to your sales or to your field application engineer within MPS of your area. Or in the presentation that we are going to share, we are going to give our emails, so you can contact us directly, or always you can contact MPS now in our webpage to contact with us. They will redirect the questions to us directly.
Yeah, so anyone can go to the contact section on the MPS website. There's a form there, and you could just put it in. We'll send out an email at the end of the week with the link to the video and to the presentation, and we'll include the direct email addresses for Albert and Miguel in that one. So that way you'll have easy access back to them. All right, we got a great session. Thank you. Last chance for questions. Anything more that hasn't been addressed that you wanted to hear about? All right, I think that's it for today. Thank you everyone for joining us. We've been doing webinars on various topics, basically about once a month. We might take a little break here in the heat of the summer, but look for webinars on a variety of topics, and hopefully we'll have another one on battery management in about the next 6 months. So once again, thanks everyone, and have a good day. Bye now.